So section 2.5 goes over the graphs of the tangent, cotangent, secant, and cosecant. And we're going to start out with this question that you're going to encounter in your homework. The graph of the tangent is symmetric with respect to the blank. So to help us with that, let's go to that link that I sent you about the tangent function. And what I did is I restricted this to just one period or one cycle of the tangent function. If you wanted to, you could add in the vertical asymptotes. This has vertical asymptotes at x equals pi over 2 and x equals negative pi over 2. So there's our two vertical asymptotes. Let me make those both green. There you go. Now this shape would continue forever and ever, but I just wanted to focus in on this part of it. So let's shut this off a little for a second or two, and then try and understand what the symmetry is. The symmetry is called origin symmetry or odd symmetry. And what goes on is that if you take this little slider and move it out, you get points that are on opposite sides of the function, and the origin is a point of symmetry, or it's kind of like in the middle of these. So let me slide this all the way out to about 1.5. And then I'm going to turn on the graph of the line that connects these. And there you go. So wherever you go in this function, if you have one point here, there's a point on the opposite side of the origin, and the origin is the midpoint. That kind of a function is called an odd function. Most of our trigonometric functions are odd functions. The tangent, the cotangent, the sine, and the cosecant. Those are all odd functions. So those would all have this kind of origin symmetry. The even functions that we're going to work with would be simply the cosine and the secant. Those are even functions. They're going to be symmetric with respect to the y-axis. So your answer to the first problem is the graph of the tangent is symmetric with respect to the origin and has vertical asymptotes at multiples of pi over 2. In fact, odd multiples of pi over 2. So if you wanted to be precise about it, it'd be 2k minus 1 times pi over 2. Those would be your odd multiples of pi over 2. All right, so let's move down to the next one, graph of the secant. Now, in working with the secant, it's probably not a bad idea to also keep in mind the graph of the reciprocal function. What's the reciprocal of the secant? Anyone?
Cosine.
Yeah, the cosine. So the cosine is going to have places where it's going to be 0. And at those places, the graph of the secant is going to have its vertical asymptotes. So they're looking at the interval from negative pi over 2 to pi, excuse me, negative 2 pi to 2 pi. And we want to know where the vertical asymptotes are. So let's click over to this graph right here. And we can look at the graph of the secant, which is this graph. And then we're slowly going to change this. Now let's see. With respect to this first one, maybe it's not a bad idea to try and understand where these vertical asymptotes are. And these vertical asymptotes are going to be places where the graph of the cosine is 0. So let me type in y equals cosine of x. And wherever the cosine is 0, that's where you're going to have a vertical asymptote for our graph. And let me just kind of zoom out a little bit on that maybe. That looks a little bit better. So it's a nice way to predict where the graph of secant is going to have its vertical asymptotes. And if you're sticking strictly for the interval negative 2 pi to 2 pi, then there's going to be 1, 2, 3, 4 vertical asymptotes, precisely where the cosine is equal to 0 in that interval. So you can just list them all. If you had to write it in general terms, in general, it's going to be those odd multiples of pi over 2. So we did something like this the other day. Let me remind you, if my software will cooperate. Come on. Focus, thank you. So in general, it's going to be 2k plus 1. Now that's going to give you all your odd numbers. Twice a number is going to be an even number, plus 1 is going to be an odd number. That times pi over 2. Okay. That's where you're going to have your odd multiples of pi over 2. You could also write it as 2k minus 1 times pi over 2 is again going to give you the same thing. If you're adding 1 or subtracting 1, you're still going to get 2 negative numbers. For what numbers does cosecant equal 1? Okay, well, we'll take a look at that. The nice thing about Desmos is that you can graph the cosecant directly. So let me shut off these other graphs. I do want to look back at those in just a little bit. Y equals cosecant of x. We want to know where the cosecant's equal to 1. Well, in working with the cosecant, we can also think of its reciprocal function. What's the reciprocal of the cosecant?
1 over sine.
Yeah, it's a reciprocal of sine. Thank you both. So there we go. Now, if I want to know where the cosecant is equal to 1, that's going to be precisely where the sine is equal to 1. So let's just look at the sine function. Sine is going to equal to 1 at these points. And that's it. You're just looking in the interval negative 2 pi to 2 pi. So there's going to be 2 places. Where does it equal negative 1? Well, there's going to be another 2 places. And it's going to equal negative 1 where the sine is equal to negative 1. So let's take a look at the sine graph. Where does the sine equal negative 1? Down here and down here. Now I feel a little bit uneasy about just relying on Desmos for this because this is just so nice. It just tells you where these things are. You might not always be able to use Desmos on future tests and future exams, etc. So let's take a look at what that would be in the graphing calculator. Let me clear all this out, clear this out. I'm going to start by graphing y equals 1 divided by sine of x. I'm also going to throw in the graph of sine of x, because that one's going to be friendlier to deal with, perhaps. And now I'm going to adjust my window size. And this time, my window's going to be a little bit prescribed based on the function that or it's going to be the interval that they gave us. So it's going to be from negative 2 pi on the x-axis. And as soon as I hit the enter key, this is going to be replaced by negative 6.28, etc. And likewise, 2 pi up here. It might be helpful to make your tick marks at specific units, like maybe pi or pi over 2. It's up to you. I'm going to do pi over 2 in this case. So I'm going to put tick marks on the x-axis at units of pi divided by 2. And that's just going to help me count special points. For the y-axis, I'm not going to hit the zoom fit key because it's probably going to squish things too much. In my case, I'll just go from, say, negative 1.5 on the y-axis to 1.5 again on the y-axis, scale of 1. Make sure that you're in radian mode for this. When you're ready, hit the graph key, and you should get a nice graph with a bunch of cups faced up and a bunch of cups face down, and then a sine graph in between. So there's your sine graph in between, pretty nice. And you can see that there's points where the graph is at negative 1, and positive, or excuse me, -1 and +1. You can also count out where that's at. Our tick marks on the x-axis were in units of pi/2. So that's pi/2, and that's 2 times pi/2, or basically pi, and that's 3 times pi/2, and then 2 pi. So it's kind of nice that we scaled it with those kind of tick marks. This would be -pi, it's gonna be -pi/2, -pi, -3 pi/2, and -2 pi. Nice. So again, you can kind of solve it just by looking at the graph. Let's keep going. So far, so good with those first few?
Yep.
Yeah.
Thank you. It says graph the following function, show at least 2 cycles. Use the domain, excuse me, use the graph to determine the domain and range of the function. Well, there's something interesting about the tangent function that makes it different than your sine, cosine, secant, and cosecant graphs. Beyond just a shape is its period. So the period of the tangent graph isn't 2 pi. Anyone pick up what the period of the tangent graph is?
Pi.
Yeah, it's pi. Good. So let's shut this off. And we're going to go up here and graph the tangent of pi/15 times x. So I'll turn that one on. And I'm going to zoom out. I'm just going to hit the home button to help zoom out. That gives me a default kind of zoom. And that didn't zoom out. It actually zoomed in a little bit. So let me zoom out. Now earlier I changed the scale on this to be in units of pi. That's not really convenient for this graph. So I'm going to change the scale again. I'm going to put tick marks every unit. So I'll make that a 1. Okay, that looks a little bit better. And let's see if we can't figure out some things about this graph. Well, what we have to do is we have to figure out the period of this graph. And there's a couple ways we can do it. Maybe what we'll do is we'll figure it out in theory, and then we'll confirm it with the graph, which is probably a good plan, because that way the graph can tell us that we're right. So let's look at y equals tangent of pi/15 times x. The period of y equals a tangent of bx is pi/b. In other words, just like the sine function, this is going to divide the period. So for our particular example, that's going to be pi divided by pi/15. That's going to be our period. To help simplify this, maybe you want to write it as pi/1 times pi/15. Does that help me out at all? Can someone suggest why that might help me out? When you divide fractions, what do?
Multiply by the reciprocal.
Yeah, and the reciprocal in this case could be 15 over pi. By putting a 1 there, I've got a fraction and another fraction. I can deal with them in terms of the reciprocal. So thank you. Does anyone see a nice way that this will simplify?
15 is the answer.
Perfect. The pi's cancel. You're left with 15 over 1, or better yet, as Durade said, just 15. Nice. How are we going to be able to tell from our graph that it's actually 15? What does it mean for something to have a period of 15? Can someone put that into words?
Just how long it takes to repeat itself, right?
Yeah, it's how long it takes to repeat itself. Thank you, Pat. So tell you what, how about if I click right here and I've got a spot on the origin, and let's figure out when that graph repeats itself. And it repeats itself maybe, I don't know, right there. How far apart are those points?
15.
15. Thanks, Zach. So yeah, it matches our predictions. So what you're gonna have to be careful of when you're working with these kinds of problems is that tangent and cotangent have a period of pi, whereas everything else has a period of 2 pi. So period of pi, tangent of x, cotangent of x. Period of 2 pi would be cosine, sine, secant, and cosecant. So just keep those in mind. There's a couple basic differences regarding the graph of the tangent and cotangent. All right, we'll finish up with a couple more here. Graph the following, show at least 2 cycles. Determine domain and range. So that's a good one. Let's take a look at this one. Y equals -8 secant x. What I'm going to do is I'm going to build this graph up slowly using translations and stuff like that. So I'll shut this one off. I guess I could have turned on the asymptotes for that graph. That's okay. And let's look at the graph of the secant. It's like this. A little bit busy. Maybe if I hit the home button, that can clean things up a little bit. So there's the graph of the secant. Great. But I want the graph of -8 times the secant. And so what I want to do is I want to show you bit by bit the effects of these things. The first thing is going to be to multiply by 8. Now that's going to stretch the graph away from the x-axis. Instead of having points here at 1 or down here at -1, those points are going to get multiplied by 8. So instead of 0, 1, where am I going to find my y-intercept? 0 and
8.
8 in the new graph. So can't even see it there. Let me zoom out for you. And I'll do it this way. Just by, yeah. Come on. If you hit the shift key, you can zoom in on just one axis or the other. So I'm hitting the shift key. I'm trying to zoom in on just the y-axis, and it's not letting me. Why is that not happening? Decimals is failing me. This doesn't happen very often, but it does occasionally. It's not letting me zoom in on just the y-axis. When it's got a sideways arrow, it kind of zooms out altogether, but here it's letting me zoom out on the x-axis. I need to do the same thing on the y-axis. It's just not happening. I don't know why. All right, so I'll just zoom out like this. But you can see what's happened by multiplying by 8, I've stretched these things. They're no longer going from 1 to infinity, they're going from 8 to infinity. And on the bottom side of things, instead of starting at -1, they start at -8. Let's get rid of that. So it just kind of stretched the graph a little bit. What do you think the addition of that negative out in front of everything is going to do? How is that going to affect the graph? What does multiplying by a negative generally do to our graphs?
Flip it upside.
Yes. So it's going to flip it. And there's your graph. So again, let me zoom out a little bit. And it's making me a little bit dizzy, so I'm just going to shut off one of these. Shut off the red one. There's your graph. Now there's 2 things that we need to know here. One of them is we need to know the range. Now the range of values, the y values, start at 8 and go up, and then start at -8 and go down. So we need to capture both parts of that. Which one of these choices here, the first one, second one, third one, or the fourth one?
Fourth one.
Bingo, fourth one. So we want the set of y's that are greater than -8. No, sorry.
The first one?
Yeah, the
Or
first
the
one.
second one? The second one?
Yeah, the second one. There we go. Second one. So we want things that are less than or equal to -8 or greater than 8, greater than or equal to 8. So that's the correct one right there. This never happened. Beautiful. And finally, the domain here is going to be the same as the domain of the, excuse me. Yeah, it's going to be the same as the domain of the secant. That is, what we're going to have to throw out are points where the cosine is 0. And we've done with that before. That's going to be your odd multiples of pi over 2. So let's see here. So our range is going to be y is less than or equal to -8, or y is greater than or equal to 8. Your domain is going to be all reals except 2k plus 1 times pi over 2, where k is an integer. And again, that's just your odd multiples of pi over 2. Any comments on that one before I hit the last one? All right. So let's hit the last one then. And that's going to be the graph of 5 secant of 1/4 x. It says show at least 2 cycles, determine the function, determine the domain and range of the function. So let's work the range part first, because it's going to look a little bit familiar to what we just dealt with. I'm just going to put it in here as y equals 5 secant of 0.25x. So 0.25 is me being lazy and not typing in 1/4. That's okay. If you were stuck doing this on a graphing calculator, how would you have to input this function? What would I be putting in right here?
1/5 cosine.
Excellent. 5 over cosine of 0.25x. Thank you. So it looked like this: 5 divided by cosine of 0.25x. And then you set up your windows accordingly. But let's go back to Desmos, take a look at things there. We'll start with the easy part first, the range. By multiplying by 5, you're stretching this graph away from the x-axis. There's a big gap here. You can see that gap. You can fill it in if you type in y equals 5 cosine of x, or cosine of 0.25x. Basically, it's reciprocal. So this is living where the gap is. But if I take that out, I can determine the range now. Y equals 5 secant 0.25. Does anyone want to take a shot at the range?
-5 and 5.
-5 and 5 play a big part of it.
Well, anything smaller than -5 and greater than 5.
So something like this. We've got everything less than or equal to -5 and everything greater than or equal to +5. So that would be your range. Oops, there should be an X in here.
So it can't be any numbers between 5 or -5?
Yeah, there's kind of a big hole. If you were to look at this graph, it is missing a chunk. And the chunk that it's missing, let me put this in red to show you the chunk that's missing, but that's the piece that's missing. If I shut this off, there you go. There's a hole where this graph lives. I'll put that back on, shut that off. Yeah, you're exactly right. It's missing that piece. Now, something else that's missing is some spots that around this point and this point vertically.
Asymptotes?
Yeah, the asymptotes. We've got to figure out where those asymptotes are for this new graph. So, okay. Now, where did the cosine have, just the cosine, not cosine of 0.25x, where did the cosine have its asymptotes? Remember, I've said it a couple times today.
Where it's a 0?
Well, the secant's going to have asymptotes where this is 0. So yeah, I guess I said, where does the cosine have asymptotes? No, that's wrong. Where does the cosine equal 0? So you're right, Durade. Where does the cosine equal 0?
When pi over 2 plus n pi.
Yes. So at odd multiples of pi over 2 plus odd multiples of pi over 2. So this function is going to have asymptotes. So y has asymptotes when cosine of 0.25x equals 0. This is going to be true when this is an odd multiple of pi over 2. When 1/4 x equals 2k plus 1 times pi over 2. How do I solve this? How would I solve for x? No one? Just help me get x by itself?
It'll be 2k plus 1 pi over 2 times 4.
Thank you. We're just going to multiply both sides by 4, right? Multiply by the reciprocal. In this case, 4. And on the left-hand side, I get x. On the right-hand side, I just get 2k plus 1 times pi. And that's going to cancel and leave me with 2. So basically, odd multiples of 2 pi. So I'll just put that all out in front. 2 pi times 2k plus 1. Or the other way around, 2k plus 1 times 2 pi. It doesn't matter. I guess in hindsight, I kind of like it like that. Odd multiples of 2 pi. Now, just to maybe show you what I mean here, let's pick a few values for k. Just to go through these and understand what's going on here. So if we let k equal 0, 2 times k plus 1 is 1. If k equals 1, 2 times 1 plus 1 is 3. Or 5. Or -1. Or -2. And if I wanted to look at this a little bit closer, odd multiples of 2 pi, 2k plus 1, 2 pi, that's going to be this number times 2 pi, so -6 pi, -2 pi, How about, yeah, negative 2 pi, 2 pi, 2 pi. Should be pi there. 6 pi and 10 pi. So these are the places that I would expect to see vertical asymptotes. And they're different from each other by 4 pi. So let's just do 1 or 2 of these. We'll do x equals 2 pi. There's 1. And x equals negative 2 pi. And there's another one. So our asymptotes are just where we thought. All right. Any comments or thoughts on this one before I put you into breakout rooms? Okay. Good luck with them, and we'll see you in a bit.